Our modern world rests on foundations laid thousands of years ago. This video uncovers 23 ingenious tools from antiquity that form the bedrock of everything we build today. You will discover the hidden engineering principles inside your smartphone and your car that were first imagined by ancient innovators. How did a simple spiral device from Greece lead to modern water treatment? And what does a Roman plumbing part have to do with space station hardware? By the end, you will see the everyday world through a new lens, spotting the fingerprints of ancient engineers on the technology you use right now. What forgotten invention do you think is most vital to your daily life? Fields of golden grain once depended on a simple spiral turning inside a wooden cylinder. Ancient farmers watched water climb steadily uphill, defying gravity to nourish their crops. This was the Archimedes Screw, a device so elegantly simple it has never really become obsolete. Attributed to the Greek mathematician Archimedes around the 3rd century before the Common Era, its genius lies in a helical surface encased within a hollow pipe. When you rotate the entire assembly, the spiral acts like a moving staircase for water, lifting it from a lower source to a higher channel with minimal effort. This was one of humanity's earliest masterpieces of fluid management, a revolutionary tool that turned arid landscapes into fertile ground. Historians like James Burke point to this invention as a foundational demonstration of hydraulics and mechanical advantage. It proved that with the right geometry, you could achieve a tremendous output from a relatively small input of energy. The screw was not just for water either. It soon found use in ancient Egyptian irrigation and later in the deep mines of medieval Europe, where it lifted not just water but slurry and ore from the depths. The core principle is all about reducing friction and energy loss, a concept that speaks directly to modern engineers. Today, that same twisting motion powers industrial augers that move grain and powders. It is at the heart of sophisticated wastewater treatment plants, gently lifting raw sewage for processing without damaging the delicate bacterial cultures needed to break it down. You can even find adaptations in fish farms where special screws transport live fish safely between water levels, and in renewable energy where micro-hydro turbines use the reverse principle, generating power from flowing water. How many of our modern challenges, from sustainable agriculture to efficient material handling, could be met with a re-examination of this ancient twist? It is a tool that connects the toil of an ancient farmer to the calculations of a modern engineer, proving that some solutions are truly timeless. And just as the screw mastered the flow of water, another ancient innovation would learn to bear immense weight, forever changing the skyline of human civilization. Those stone channels marching across the landscape were far more than just monuments. They were the lifeblood of an empire, a network of arteries delivering fresh water to the heart of Rome and its distant provinces. The sheer audacity of the Roman aqueduct is staggering, a testament to an engineering culture that refused to be limited by geography. Imagine a channel, often just a gentle groove in stone, carrying water for dozens of miles without a single pump. The secret was a relentless, calculated downhill slope. Roman engineers like Vitruvius perfected a gradient of just a few feet per mile, a slope so slight it is almost imperceptible to the eye, yet it was enough to keep water flowing steadily from mountain springs to city centers. This was gravity-fed hydrology on a grand scale, but the true genius was in the details. They did not simply build straight lines. They integrated inverted siphons to carry water across deep valleys, used settling tanks to let silt and debris fall out of the flow, and built complex distribution networks with lead or ceramic pipes to control pressure and direct water to its final destinations. The public baths, the countless fountains, even the private homes of wealthy citizens all relied on this constant, clean supply. It was a system that enabled unprecedented urban growth and public health, a luxury that would not be seen again in Europe for over 1,000 years. Their choice of materials was just as forward-thinking. They used a special concrete made with pozzolana ash, a volcanic dust that reacts with seawater to form an incredibly durable binder, allowing their arches and piers to stand for millennia. Look at our modern world, and you will see the same principles alive and well. The California Aqueduct, a serpentine concrete river quenching the thirst of a state, operates on the very same rule of gravity. Our municipal water grids, with their settling basins and pressure-regulating valves, are direct descendants of that Roman blueprint. So what can these ancient waterways teach us about our own future? As global water scarcity becomes a critical challenge, perhaps the answers lie not in reinventing the wheel, but in revisiting the elegant, efficient flow of the aqueduct. While the Romans mastered the movement of water on a massive scale, another ancient innovation was perfecting the manipulation of solid matter, one precise turn at a time. Precision was born from a spinning axis. Deep in an ancient Egyptian workshop, a craftsperson would have guided a sharp tool against a piece of wood rotating rapidly between 2 points. This was the lathe, a machine that harnessed circular motion to sculpt symmetry from raw material. Originating as early as 1,300 years before the Common Era, this tool transformed how humanity shaped the world. The Greeks and Romans later refined it, adding foot pedals to free both of the operator's hands for meticulous control. This seemingly simple device, described by historians like Pliny the Elder, was a quiet revolution. It allowed for the creation of perfectly round table legs, elegant pottery wheels, and the first standardized components. The principle was pure genius. By rotating the workpiece instead of moving the tool in a circle, the lathe achieved a level of consistency and detail that hand carving could never match. Its evolution was a cascade of innovation. The bow lathe used a wrapped cord pulled back and forth, while the spring pole lathe stored energy in a bent sapling for a more continuous cut. For centuries, these machines produced the vital components for clocks, musical instruments, and scientific devices. Then, steam power was applied, turning this ancient tool into the roaring heart of the Industrial Revolution, mass-producing parts for the new age of engines. The fundamental mechanics remain unchanged today. A workpiece spins, and a stationary cutting tool peels away material with breathtaking accuracy. This direct interaction is the bedrock of all modern machining, from the computer-controlled lathes, or CNC machines, that carve aerospace components with micron-level precision, to the automated factories that fabricate every piston and bolt in your car. The journey from a craftsman's foot pedal to computer code is one of the most direct lineages in engineering history. It prompts a powerful question. How many of our advanced technologies are not replacements for ancient tools, but rather their ultimate evolution? This ancient mastery of shaping individual parts would be useless, however, without an equally ancient method for locking them perfectly together. That screw spinning into its nut creates a bond stronger than the material itself. This simple act of threading one piece into another gave ancient builders a power they never had before, the ability to fasten materials securely and to adjust tension with perfect precision. While early versions appeared in Greek and Assyrian devices like olive presses, it was Archimedes who formalized the principle of the helical incline. The Romans, pragmatic as ever, then standardized the nut, using these threaded pairs to assemble their siege engines and architectural frameworks with a new level of strength and reliability. The screw is essentially a wedge wrapped around a cylinder, a brilliant application of mechanical advantage that allows a small rotational force to generate an immense linear clamping force. This fundamental action of converting rotation into a powerful straight-line push or pull is what makes a screw so incredibly versatile. It is the hidden heart of the adjustable clamp that holds your project steady, the intricate gear train in a mechanical watch, and the complex propulsion systems of modern aircraft. The real revolution came during the Industrial Revolution, when engineers finally standardized thread pitches. This meant a nut made in one factory would fit a bolt made in another, a concept that seems obvious to us now but which unlocked the era of mass production and interchangeable parts. Look around and you will see this ancient principle holding your world together. It is in the adjustable legs of your desk, ensuring it stands level on an uneven floor. It is in the titanium screws used in surgical implants, fusing with human bone to provide stable support for a lifetime. From the massive steel bolts holding a suspension bridged together to the microscopic threads inside your smartphone, this is the unsung hero of engineering. How many of the devices you rely on would simply fall apart without this ancient innovation? It is a testament to a simple truth that the greatest strength often lies not in a single solid piece, but in the clever, reliable connection between pieces. And just as the screw mastered the art of holding things together, another ancient tool would conquer the challenge of moving them. A single rope passed over a grooved wheel could lift a weight far heavier than any person could manage alone. This simple redirection of force was a revelation to the ancient builders of Egypt, who used rudimentary pulley systems to hoist the colossal limestone blocks for the pyramids. By threading ropes over wooden wheels, they effectively traded distance for effort, pulling a long length of rope to move a heavy object a much shorter distance, but with a fraction of the strain. This fundamental principle of mechanical advantage did not emerge in just one place. It was discovered and refined independently in the workshops of Mesopotamia, the harbors of Greece, and the courts of China, each culture recognizing the power of redirecting tension. Greek thinkers like Aristotle and later Hero of Alexandria documented the physics, explaining how a system of multiple wheels could multiply lifting power exponentially. A compound pulley with one rope weaving through several wheels, some fixed and others movable, could allow a small team to lift loads that would otherwise require hundreds. This was not just about raw power, it was about intelligent force distribution. The same principle tightened the rigging on ancient sailing ships, allowing crews to adjust massive sails against the wind, and it drew heavy buckets of water from deep wells with surprising ease. This ancient understanding of work and energy conservation is the unspoken hero in countless modern machines. Look at the towering cranes that stitch skylines together, their steel cables weaving through massive blocks and tackles to lift prefabricated rooms dozens of stories high. Step into an elevator and you are experiencing a pulley system, a smooth ascent powered by cables looped over a motorized sheave. Even the weight machine at your local gym uses pulleys to redirect resistance, giving you a controlled and efficient workout. From the complex rigging that flies actors across a theater stage to the rescue systems that carefully lift people from crevices, the logic of the pulley is everywhere. It makes you wonder how many of our modern logistical nightmares could be untangled by revisiting this elegant principle of redistributing force. The ability to lift massive objects transformed construction, but it was a companion tool that ensured every block was perfectly placed, every structure perfectly aligned. Precision was not just an idea, but a physical tool held in the hand. a Roman engineer would have carefully placed the hinged legs of a caliper across the outside of a clay pipe, feeling the metal jaws meet the surface to confirm its diameter was exactly right for the aqueduct network. This simple act of comparative measurement was a quiet rebellion against inconsistency, a commitment to standards that would allow parts crafted miles apart to fit together perfectly. Early versions of this tool, discovered in Chinese tombs and Greek shipwrecks dating back to the 6th century before the Common Era, were marvels of practical geometry. They came in two forms, one for gauging the outside of an object and another, with curved legs, for reaching inside a bore or a hollow vessel. This dual capability brought unprecedented accuracy to metalworking, carpentry, and sculpture, ensuring that a helmet would fit a soldier, a wheel would turn on its axle, and a musical instrument would produce the correct pitch. Centuries later, minds like Galileo would rely on these very tools to take precise measurements in their groundbreaking experiments, laying the foundation for the science of metrology. The core principle is one of comparison. The fixed jaw and the movable jaw capture a dimension, which is then read against a scale. This method evolved from simple etched lines to the vernier scale in the 17th century, which allowed for measurements down to a fraction of a millimeter, and has now culminated in the digital caliper that provides an instant, flawless reading. This relentless pursuit of accuracy was the silent engine of industrial progress. Standardized coins enabled trade, precisely fitted armor protected lives, and interchangeable components made mass production possible. Today, on any automotive assembly line, you will find electronic calipers ensuring every piston and every brake rotor is manufactured to a tolerance thinner than a human hair. This is not merely about building things, it is about building things that work together reliably and safely. How many of our greatest technological leaps would have been impossible without this foundational commitment to measuring our world with ever greater care? This ancient drive to quantify and control our environment through precise measurement naturally paved the way for tools that could manage the immense, untamed power of nature itself. The rhythmic splash of a massive wooden wheel could power an entire village industry. Along a fast-flowing river, a water wheel turned relentlessly, its sturdy paddles catching the current to drive grindstones that crushed grain into flour. This was not just a mill, it was one of humanity's first successful harnessings of renewable energy, a direct conversion of the river's kinetic force into useful mechanical work. Originating in the Hellenistic world around the 3rd century before the Common Era, and later refined by Roman engineers like Vitruvius and independently by Chinese innovators, the water wheel came in several brilliant designs. The undershot wheel simply dipped into a stream pushed by the water's flow. The more efficient overshot wheel channeled water over the top, using the weight of the captured water in its buckets as well as the flow to generate greater power. Then there was the breastshot wheel, a compromise that struck the side of the wheel at its midpoint, balancing force and construction cost. Each design was a lesson in optimizing energy capture from a moving fluid, a principle that would one day lead directly to the modern water turbines that spin inside our hydroelectric dams. This ancient technology did far more than just grind grain. It became the primary engine for early industrialization. Across medieval Europe, water wheels powered massive hammers for forging iron, operated bellows for smelters, and ran fulling mills where heavy wooden hammers pounded woven cloth to thicken and clean it. They drove sawmills that could slice through massive logs with a speed and consistency human hands could never achieve, enabling the construction of larger ships and buildings. This was a world transitioning from pure muscle power to mechanical power, all fueled by the endless, reliable energy of a river. The legacy of that turning wheel is all around us today. The massive hydroelectric dams that provide clean power to millions are its direct descendants, their generators operating on the same fundamental principle of converting flowing water into rotational energy. In remote communities, small-scale micro-hydro projects use modern versions of the water wheel to generate electricity independently from a central grid. Even in classrooms, simple water wheel models teach students the core concepts of fluid dynamics and sustainable engineering. It makes you wonder, as we face modern energy crises, what other timeless principles of renewable power are waiting for us to rediscover in the annals of history. This ancient mastery of capturing flowing energy paved the way for another critical innovation, one that focused not on harnessing motion, but on preserving a precious resource through the art of containment. A perfectly symmetrical clay pot emerges from a spinning disc, its walls rising thin and even under the potter's guiding hands. This was the ceramic pottery wheel, an innovation from Mesopotamia around 3,500 years before the Common Era that transformed clay from a pliable substance into a precision medium. It began with the slow turn of a tournet, a simple stone disc rotated by hand, but the true breakthrough came with the kick wheel, which freed both of the potter's hands to shape the clay, allowing for unprecedented speed and consistency. This was not merely an artistic tool, it was an early engine of mass production, churning out standardized jars for grain, oil, and wine that fueled trade across the ancient world. The wheel introduced humanity to the practical power of centrifugal force, a concept we now see in the high-speed laboratory, centrifuges that separate blood plasma, and the industrial mixers that blend everything from concrete to cake batter. The rotation itself is the key, distributing the material and the internal stresses evenly in every direction, a principle modern engineers use to create incredibly strong composite materials and to press perfectly uniform pharmaceutical tablets. This ancient process also sparked a chemical revolution in the kiln, as potters experimented with glazes to create waterproof, decorative surfaces, laying the groundwork for the heat-resistant ceramics that now line jet engines and protect the delicate electronics in your smartphone. From the amphorae that carried wine across the Roman Empire to the silica tiles that shielded space shuttles from searing re-entry temperatures, the legacy of that spinning wheel is written in fire and clay. It prompts a fascinating question: how did the pursuit of a simple, sturdy pot lead us to materials that can withstand the vacuum of space? This ancient mastery of shaping vessels with rotational force paved the way for a tool that would shape entire cities, carving stone with a patient, grinding persistence. A weighted cord hanging perfectly still cuts through the chaos of a construction site. In the shadows of an unfinished pyramid, an Egyptian architect would have watched this simple device, the Plumb bob, to guarantee that every massive stone was set true to the Earth's pull. This tool, a pointed weight suspended on a string, has been the silent guardian of verticality for millennia, used from the stone yards of ancient India to the marble quarries of Greece. Its principle is gravity itself, an unwavering force that defines a perfect vertical line, a reference upon which all stable construction depends. Historical accounts of master builders like Imhotep underscore its non-negotiable role in achieving structural integrity, ensuring that monumental projects like the pyramids would not merely be impressive, but would stand for ages. The Plumb bob's beautiful simplicity belies its profound importance. A wall built just a few degrees off true can lead to catastrophic failure over time, as uneven stresses pull the structure apart. This ancient tool prevented that, one careful measurement at a time. Its use extended beyond pyramids, guiding the construction of Roman aqueducts so their channels maintained a consistent grade, and ensuring the soaring walls of Gothic cathedrals rose straight toward the heavens. This relentless pursuit of the vertical is a thread that connects the stonemason to the modern skyscraper engineer, while the tool itself has evolved into laser levels that project perfectly straight lines across a room and digital theodolites that measure angles with electronic precision. The fundamental principle remains unchanged. We still build according to gravity's dictates. This ancient logic is embedded in the GPS systems that help farmers plow straight lines across vast fields, and it is critical in roller coaster construction, where the precise vertical alignment of support columns is a matter of safety, ensuring the thrilling ride remains securely on its tracks. How is it that a tool relying on nothing more than a string and a weight can achieve such enduring reliability across thousands of years? It speaks to the power of foundational physics, a constant in our lives that we can build upon with absolute confidence. This mastery of the vertical was only half the story, for ancient builders also possessed an equally ingenious tool for defining the perfect horizontal plane. A flat surface is a silent promise of stability. Roman engineers, laying the vast network of roads that bound their empire together, depended on simple yet brilliant tools to guarantee that promise. They used water-filled channels, knowing that the liquid would always find its own level, or they employed a device called a corebates, a long wooden frame with plumb bobs hanging from each end. If the bobs aligned with marked lines, the surface was perfectly horizontal. This pursuit of the plane was just as ancient as the pursuit of the vertical. The Egyptians had their own version, the Merkit, which used a similar gravity-based principle to ensure their irrigation canals delivered water evenly across fields. These tools embodied the physical principle of equilibrium, a state of balance where forces cancel each other out. It is a concept that is absolutely vital for everything from laying the foundation of a house to calibrating the sensitive machinery that builds microchips. Without a true level, the most ambitious structure is doomed to fail. The evolution of this tool is a story of refining that search for balance. The corebates gave way to the spirit level, a sealed vial of liquid with a single air bubble that floats perfectly to the center when the tool is placed on a level surface. This simple handheld device became a universal symbol of the builder, used for everything from hanging a picture frame to aligning the massive concrete girders of a highway overpass. Today, that evolution continues with laser levels that project a perfectly straight, bright line across an entire room, and with sophisticated digital inclinometers that provide a precise numerical readout of any angle. The legacy of these ancient tools is written into the world around us. The incredibly gentle, consistent slope of a Roman aqueduct, which dropped only a few feet over a mile, was achieved with these early levels. The vast, flat floors of medieval cathedrals, which support thousands of tons of stone, were verified with them. Modern surveying instruments, which map entire cities and plot the course of new infrastructure, are their direct descendants. And the applications have expanded far beyond construction. The print bed of a 3D printer must be perfectly level to ensure the first layer of plastic adheres correctly, otherwise the entire print fails. A satellite dish needs precise leveling to achieve the best possible signal from a spacecraft orbiting thousands of miles away. It makes you wonder, does this ancient drive for a level foundation mirror a deeper human desire for balance in our own lives? Just as a structure cannot stand on an uneven base, perhaps our own endeavors require a similar equilibrium to truly endure. This meticulous attention to flat surfaces and perfect angles was made possible by another tool, one that could inscribe those precise marks directly onto the hardest materials. The sharp ring of metal on stone echoes through history, a sound that built civilizations from the ground up. A Greek sculptor would have gripped a bronze chisel, its edge hardened by a master smith, and with careful, deliberate strikes, transformed a featureless block of marble into a flowing garment or a lifelike muscle. This was not a tool of brute force but of supreme control. Originating in the Bronze Age, the chisel in its various forms, from flat blades for smoothing surfaces to pointed picks for roughing out shapes, gave humanity dominion over the hardest materials. Stonemasons through the ages developed a whole family of these tools, each with a specific purpose for undercutting, detailing, or texturing. The underlying physics is pure genius. The chisel is a wedge concentrating the force of a hammer blow into an incredibly narrow line, creating immense pressure that cleanly parts the material's crystalline structure. This principle of focused force is what allows a modern surgeon to perform an osteotomy, using a surgical chisel to make precise cuts in bone without shattering the surrounding tissue. It is the same action that drives a diamond-tipped concrete saw through a highway or an engraver's beren to trace intricate lines on a piece of jewelry. This ancient tool has evolved dramatically while retaining its core identity. The hand-powered mallet and chisel gave way to the pneumatic hammer, which delivers a rapid series of impacts that can break apart rock or delicately carve a decorative frieze. Today, we see the ultimate expression of the chisel in computer-controlled routers, which automate that same cutting action with microscopic precision, sculpting everything from custom cabinetry to aerospace components from solid blocks of aluminum or composite materials. This progression prompts a fascinating question. How do the manual skills of a master carver, the feel for the material's grain and resistance, inform the algorithms that guide our digital fabrication tools? The legacy of the chisel is a testament to the enduring human desire to shape our world with intention and artistry, one precise cut at a time. And just as this tool mastered the careful removal of solid matter, another ancient invention would achieve an even finer control over the movement of liquids. A bronze plug carefully turned by a Roman aqueduct keeper could redirect an entire river's worth of water from a public bath to a distant neighborhood fountain. This was the early valve, a device of simple yet profound intelligence that gave engineers command over the very flow of life. Developed independently in the sophisticated plumbing of Minoan palaces and the sprawling Roman water networks, the valve introduced a new idea that a fluid's path could be started, stopped, and metered with precision. The most common design was the plug valve, a conical stopper seated inside a matching housing. A quarter turn could seal a pipe completely, a revolutionary concept for managing resources and preventing dangerous backflows in complex systems. Engineers today point to these ancient designs as the origin of pressure management. The precise machining of that conical plug against its bronze seat created a seal that could hold back significant water pressure, a principle absolutely critical in everything from your home's plumbing to the immense pipelines that cross continents. This was not just about convenience, it was about control and safety on a grand scale. The evolution of this idea is a story of refining that seal and the mechanisms that operate it. The simple plug valve gave rise to the gate valve, which uses a solid wedge lowered across the flow, and the ball valve, with its rotating sphere featuring a single hole. Each design offers a different balance of sealing capability, speed of operation, and durability. Today, you will find these principles scaled to every conceivable size and purpose. A massive gate valve in a hydroelectric dam can be larger than a house, controlling a torrent with the push of a button. In a hospital, a microscopic solenoid valve, an electrically operated marvel, can dispense precise droplets of medication into an intravenous line. This ancient tool even made early steam power possible, as seen in Heron of Alexandria's Eolipile, a primitive steam turbine that used valves to direct jets of steam. Its most profound modern parallel, however, may be inside the human body. The artificial heart valve is a direct descendant of this ancient technology, a mechanical gate that replicates the function of a biological valve, opening and closing with every heartbeat to sustain life itself. It prompts a powerful reflection. The entire discipline of engineering, and perhaps life itself, often comes down to learning how to control flow, whether it is water, energy, information, or even personal change. Knowing when to open a path and when to close it is the essence of management and growth. And just as the valve gave us mastery over fluid forces, another ancient tool would unlock the power to amplify our own physical strength for the most monumental tasks. A long wooden beam resting on a single stone could lift a weight that defied 100 strong backs. This was the lever, a tool of such profound simplicity that it feels almost elemental. While often attributed to the Greek mathematician Archimedes, who famously declared he could move the world with a lever long enough and a place to stand, its use predates him by millennia. Ancient Egyptian workers employed massive levers to precisely position the multi-ton blocks of the pyramids, and the mysterious architects of Stonehenge likely used the same principle to raise their towering monoliths. The lever operates on the principle of torque, a turning force, by placing a pivot point or fulcrum close to the massive load you wish to move. A small force applied over a long distance on the other end of the beam is transformed into a massive force that moves the load a short distance. This is mechanical advantage in its purest form, a brilliant trade of distance for power. The ancients formalized this into three distinct classes. A first-class lever has the fulcrum in the middle, like a seesaw or a crowbar prying up a heavy rock. A second-class lever places the load between the effort and the fulcrum, the principle behind the humble wheelbarrow that lets you carry a heavy load with ease. A third-class lever has the effort applied between the fulcrum and the load, which sacrifices pure power for speed and range of motion, exactly like using a pair of tweezers or swinging a baseball bat. These variations were applied everywhere. The shadoof, an irrigation tool used along the Nile for thousands of years, was a first-class lever with a counterweight, allowing a single farmer to lift heavy buckets of water from the river to higher fields with minimal strain. Roman siege engines used massive levers to fling projectiles, and ancient scales for trade relied on the balanced lever to ensure fairness. The evolution of this principle is a story of amplifying human capability. The simple crowbar is a direct descendant, as is the hydraulic jack that lifts an entire car by using fluid pressure to create an immensely powerful lever action. In modern robotics, the joints of a robotic arm are precisely controlled levers, allowing for delicate assembly work in factories. Even at the gym, the weight machines you use rely on lever systems and adjustable pulleys to provide smooth, consistent resistance, making strength training safer and more effective. This principle of leveraging small efforts for great outcomes transcends engineering, finding a home in economics with the concept of financial leverage, where a small amount of capital can control a large asset. It invites a powerful question for our own lives. In what areas can we find our own fulcrum, that strategic point of support, to amplify our efforts and achieve far greater results? This ancient tool of amplification set the stage for another invention, one that would learn not just to multiply force, but to store it for explosive release. A simple bronze strip flexing rhythmically beneath a trader's wagon smoothed a journey across a rocky path. This was the leaf spring, an ancient innovation from Celtic and Roman cultures that turned punishing jolts into manageable vibrations. But springs were more than just cushions. They were the first reliable method for storing mechanical energy. The principle of elasticity was harnessed in various brilliant forms. In ancient Greece, the torsion spring used the twist of a sinew rope to power deadly catapults, while in China, bronze leaf springs made crossbows more powerful and easier to reload. These devices all understood a fundamental physical truth, that deforming a material within its elastic limit would make it want to snap back to its original shape, releasing the energy you put into it. This is the conversion of potential energy into kinetic energy, a concept that would become the heartbeat of mechanical automation. Historical sketches by inventors like Leonardo da Vinci reveal intricate spring-driven mechanisms designed for everything from automated lions to precise clocks, demonstrating how this stored energy could be metered out in controlled, repeatable motions. The evolution of the spring is a story of refining this storage and release. The coiled metal spring, which packs immense potential energy into a compact spiral, was a breakthrough that revolutionized timekeeping, allowing for portable watches and accurate marine chronometers. Today, this ancient principle of elastic potential is absolutely everywhere. It is in the suspension of your car, where a combination of springs and shock absorbers transforms a bumpy road into a smooth ride, protecting both the vehicle and its passengers. It is in the humble retractable pen, where a small spring provides the satisfying click that advances and retracts the ink cartridge. On a much larger scale, seismic dampers in skyscrapers use massive, sophisticated spring assemblies to absorb the violent energy of an earthquake, swaying to dissipate forces that would otherwise shatter the building's rigid frame. Even the tiny tactile switch beneath your keyboard key relies on a microscopic spring to give you that responsive click and to complete an electrical circuit. This progression from a wagon's suspension to a building's seismic protection invites a deeper reflection. How does the ability to store energy efficiently and then release it in a controlled manner lie at the heart of both technological and personal resilience? It is a principle of adaptation, of absorbing impact without breaking, and of using stored potential to power our next move. This mastery of controlled energy release through elasticity paved the way for a tool that would bring a new kind of order to motion, one precise tick at a time. Interlocking bronze gears recovered from a 2,000-year-old shipwreck calculated the future positions of the sun and moon with breathtaking accuracy. This was the Antikythera mechanism, a complex astronomical computer from ancient Greece that relied on a network of precisely cut gears to model the cosmos. Its discovery revealed a level of mechanical sophistication that historians once believed was impossible for its time. The fundamental principle of the gear is one of transformation, taking a source of motion and altering its speed, direction, or force. A small, rapidly spinning gear can turn a large, slow-moving gear with immense power, or the reverse can be true, trading force for speed. This simple act of meshing toothed wheels allowed ancient engineers to build water mills that could grind grain with optimal efficiency and to construct intricate odometers that measured the distance traveled by Roman chariots. Scholar inventors like Hero of Alexandria described complex gear trains in his designs for automated puppet theaters, demonstrating an early grasp of ratios and synchronization. The gear's true genius lies in this predictable, mathematical relationship. The number of teeth on one wheel compared to its partner dictates the exact ratio of their rotation, a principle of mechanical harmony that is the bedrock of all automated machinery. This ancient logic is what allows a modern 10-speed bicycle to conquer a steep hill, the rider shifting the chain across gears of different sizes to find the perfect balance of pedal effort and wheel rotation. It is the heart of the planetary gearbox inside a wind turbine, managing the wildly variable spin of the massive blades to generate a consistent flow of electricity. In the precise world of a mechanical wristwatch, a tiny forest of minuscule gears, or a gear train, translates the unwinding of the mainspring into the steady sweep of the second hand. This principle of interlocking components extends far beyond metal. The synchronized movement of a robotic arm on an assembly line, placing components with sub-millimeter accuracy, is a digital echo of those ancient gear trains. How often do we see this same principle in our own lives, where the harmonious meshing of different skills and personalities within a team can achieve outcomes far greater than any individual could alone? This intricate dance of moving parts, creating unified action from separate forces, set the stage for a tool that would conquer a different kind of challenge, providing a stable foundation for movement across the most unpredictable landscapes. That fixed axle and rotating wheel created a new kind of symmetry, one that could travel. While the pottery wheel shaped clay, the true revolution came when Mesopotamian innovators around 3,500 years before the Common Era mounted a solid wooden disc onto a central pin, creating a system that would literally move civilization forward. This was not merely a rolling log, but a carefully engineered pair, the wheel and axle, a single rigid unit that fundamentally redefined friction. By concentrating the load on the fixed axle, which rotated within a lubricated housing, the system minimized the surface area in contact, allowing the much larger wheel to roll freely with vastly reduced effort. This simple machine, as experts in mechanics explain, is essentially a perpetual lever, with the axle acting as the fulcrum and the wheel's radius providing the mechanical advantage. A small force applied to the rim of the wheel generates a powerful rotational force on the axle, or vice versa. This principle of rotational force was immediately harnessed for transportation, transforming the chariot into a weapon of war and the cart into an engine of commerce, enabling the movement of goods and people on a scale previously unimaginable. But its use was not limited to the road. The same combination powered the massive Norse grinding mills known as querns, where a horizontal axle turned a heavy upper stone against a stationary lower one. It was the driving force behind the sakia, an ancient water-lifting device that used a geared wheel turned by an animal to raise water from wells for irrigation. The true genius of this invention lies in its dual nature, its ability to both bear immense weight and transfer energy efficiently. Look at any modern vehicle and you see this ancient partnership at work. The axle transmits power from the engine to the wheels, while the tires themselves are marvels of material science, their carefully engineered contact patches minimizing rolling resistance just as the first wooden wheels did. This principle scales from the smallest precision bearings inside a computer hard drive, which allow the platters to spin thousands of times per minute with almost no friction, to the colossal rotor assemblies in wind turbines, where the entire nacelle turns on a massive axle to face the wind. Even the simple doorknob in your home is a perfect example, a small wheel on an axle that multiplies your hand's torque to easily retract the heavy latch. From the sturdy wheels that carried Roman legions along their famed road networks to the complex, shock-absorbing landing gear that safely touches down a modern aircraft, this ancient idea of circular motion remains the unsung hero of global mobility and logistics. It makes you wonder if this relentless, forward-turning motion is more than just a mechanical principle. Perhaps it is a symbol of progress itself, a cycle of innovation that continually rolls us toward new horizons. And just as the wheel and axle learned to capture motion for transport, another ancient tool would master the art of capturing light itself, preserving moments and knowledge for eternity. A darkened room became the first canvas for light itself. Ancient scholars in China and Greece witnessed a strange and magical phenomenon, a tiny hole in a wall projecting a perfect, albeit upside down, image of the outside world onto the opposite surface. This was the camera obscura, a device that proved light travels in straight lines, carrying information from every point in a scene to form a coherent picture. The Chinese philosopher Mozi documented this effect in the 4th century before the Common Era, while Aristotle used it to observe a partial solar eclipse, safely watching the crescent shape of the sun projected on the ground. For centuries, this was a fascinating curiosity, a natural trick of physics. Then, during the Renaissance, it transformed into an essential tool. Artists like Leonardo da Vinci described its use for mastering perspective, tracing the projected outlines of landscapes and architecture to achieve a level of realism that had previously been elusive. This was the moment the camera obscura evolved from a passive observation into an active instrument for capturing and understanding our visual reality. The underlying principle is beautifully straightforward. Every point in a bright scene emits or reflects light in all directions, but only the single narrow beam from each point that passes directly through the small aperture will continue in a straight line to its corresponding point on the projection surface, creating the inverted image. This foundational understanding of rectilinear propagation is what informed the development of lenses. By placing a curved glass lens over the pinhole, inventors could gather more light and focus the image with far greater brightness and clarity. This single step bridged the ancient observation chamber to the first photographic cameras, which essentially trapped that fleeting projected image onto a light-sensitive chemical plate. The legacy of that dark room is now embedded in the most advanced imaging systems we have. The complex array of multiple lens elements in a modern DSLR camera is a direct evolution of that single pinhole, each glass element engineered to correct for distortions and focus light with perfect precision onto a digital sensor. In medicine, an endoscope is a miniature camera obscura, a flexible tube with a lens at its tip that projects an image of your internal organs onto a screen for a surgeon to see. Even the powerful telescopes that peer into the deepest reaches of space operate on this same principle, gathering faint light from distant stars to form a coherent image. And consider the device in your pocket. Your smartphone camera uses a microscopic version of this entire system, a tiny lens focusing light onto a semiconductor sensor that converts the image into digital data in an instant. This journey from a dark chamber to a pocket-sized computer raises a profound question. How does the very lens through which we observe the world, whether it is made of glass or of our own preconceptions, shape our understanding of reality? The camera obscura taught us that perception is not a passive reception, but an active construction of an image from scattered rays of light. This ancient tool for capturing images through the controlled manipulation of light finds a parallel in another invention that sought to capture something even more elusive, the steady, relentless passage of time itself. The steady drip of water marked the passage of hours long before the tick of a clock. In the shadowed halls of Egyptian temples and the bustling courts of Babylon, the clepsydra, or water clock, transformed the abstract river of time into something measurable and predictable. This was not a sundial dependent on the whims of the weather, but a device that worked through the night and in any chamber, powered by the constant, gentle force of gravity on a stream of water. The simplest design was an outflow clock, a bowl with a small hole near the base and markings on its interior wall. As the water level slowly fell, it revealed these marks, each representing a unit of time. But the true engineering marvel was the inflow clock, which used a constant supply of water to raise a float within a second container. As the float rose, it could turn a gear or point to a scale, providing a clear, visual readout of the elapsed interval. This was continuous measurement in action, a concept that would become the heartbeat of all experimental science. The Greeks famously used these clocks to time speeches in their democratic assemblies, ensuring every citizen had an equal voice. Astronomers relied on them to track the movements of celestial bodies across the night sky, their observations only possible because they could trust the steady flow from their water clock. This relentless drip demonstrated early principles of fluid dynamics and calibration, as engineers learned that water flows faster under greater pressure, leading them to design tapered containers to maintain a more consistent rate as the level dropped. The evolution from this ancient timer is a direct line. The search for a more consistent regulator than water led to the swinging pendulum, the heart of the first mechanical clocks. The quest for an even more stable oscillator gave us the vibrating quartz crystal inside every modern watch and computer, and the core need for measured intervals persists in the simple hourglass timing a board game and the digital countdown on your kitchen stove. This ancient mastery of time invites a personal reflection. In a world of constant distraction, how might we apply the same principle of the clepsydra to our own lives, using deliberate, measured intervals to enhance our focus, our productivity, and even our mindfulness? Just as these clocks brought order to ancient societies, perhaps intentional time management can bring a new kind of order to our modern days. And while the water clock mastered the measurement of time's passage, another tool would be required to master the geometry of the space we inhabit, providing the precise angles needed to navigate the seas and raise our greatest structures. A brass disc etched with the constellations could guide a ship across a trackless ocean. In the hands of a medieval navigator, the Astrolabe was more than a tool. It was a portable model of the universe, a complex computer made of metal that translated the silent language of the stars into a precise location on Earth. Developed from the foundational work of Greek astronomers like Hipparchus and perfected by Islamic scholars over centuries, this intricate device combined a star chart, a rotating retar representing the heavens, and an alidade, a sighting rule, all on a single plate. To use it, a sailor would suspend the astrolabe, align the alidade with a known star like Polaris, and read the altitude from a graduated scale on the edge. This single measurement, when cross-referenced with the date on the device's intricate plates, revealed the ship's latitude, its north-south position on the globe. Scholar Al-Biruni wrote extensively on its construction and use, noting how it brought the abstract mathematics of astronomy into the practical world of navigation and timekeeping, effectively teaching an entire age how to measure the sky. The astrolabe's true genius lay in its use of stereographic projection, a mathematical method for representing the three-dimensional dome of the sky onto a flat, two-dimensional plate. This clever mapping preserved the angular relationships between the stars, allowing complex spherical trigonometry problems to be solved with a simple rotation of the retar. This very same principle of projecting a sphere onto a plane is fundamental to how we create modern maps of the world, and it is the bedrock of computer graphics that render three-dimensional environments on your flat screen. But its utility went far beyond the sea. Islamic scholars used precise astrolabes to determine the exact times for daily prayers based on the sun's position. Farmers consulted them to identify the optimal planting and harvesting seasons by tracking the sun's path through the zodiac. It was, in every sense, an analog computer for its era, a handheld device that could perform hundreds of calculations related to time, space, and the calendar. Its legacy is written in the lines of later instruments. The mariner's astrolabe evolved into the more precise sextant, which in turn paved the conceptual way for the celestial navigation systems used in early aviation. Today, the core logic of the astrolabe lives on in the triangulation algorithms that power the GPS in your phone, using signals from multiple satellites to pinpoint your location on Earth just as sailors once used multiple stars. Virtual planetarium software that lets you explore the night sky from your laptop is a direct digital descendant of that rotating Lathe. Even the guidance systems of autonomous drones use a form of celestial reckoning, comparing camera data to known landmarks to navigate. How remarkable that mapping the abstract heavens provided the key to unlocking our own planet, guiding earthly journeys with celestial certainty. This act of looking upward for direction finds a powerful parallel in another ancient tool that learned to capture an invisible, flowing force to propel us forward. A vast expanse of woven cloth could pull a wooden ship across an entire ocean. Phoenician merchants, masters of the Mediterranean, were among the first to truly master this art, turning the invisible force of the wind into a reliable engine for trade and exploration. This was the sail, an innovation so powerful it shrunk the ancient world. Its origins reach back to ancient Egypt and Mesopotamia, where simple square sails first transformed reed rafts into vessels capable of journeying beyond the river's current. For the first time, humanity was not merely drifting with the wind, but learning to capture its power and choose a direction, a fundamental shift in our relationship with nature. The evolution of the sail is a story of refining that capture. The early square sail was effective for sailing with the wind directly behind you, but it was the development of the Latine rig, a triangular sail that could be angled into the wind, that truly unlocked the seas. This triangular shape operates on the same principles as an aircraft wing, utilizing Bernoulli's principle. As wind flows over the curved surface of the sail, it has to travel a longer path over the outer side than the inner, creating an area of lower pressure in front of the sail that effectively pulls the vessel forward. This generation of lift, rather than just being pushed from behind, allowed ships like the nimble Viking longships and the massive Chinese junks to tack against the wind, exploring and connecting continents with a freedom previously unimaginable. This ancient mastery of aerodynamics is not a relic. You can see it in the sleek, towering sails of a modern America's Cup yacht, where carbon fiber wings slice through the air with engineered perfection. More profoundly, the very same principles that guided those ancient mariners are now scaled up in the massive blades of wind turbines, which use their airfoil shape to capture the wind's energy and convert it into electricity. The legacy of the sail is also experiencing a renaissance in commercial shipping. Facing rising fuel costs and environmental pressures, companies are experimenting with massive, rigid sails on modern cargo ships. These are not simple cloth sheets, but sophisticated, automated airfoils that can reduce a vessel's fuel consumption by a staggering 20%. Proving that this ancient technology still has a vital role to play in a sustainable future. From the windsurfer skimming across a lake to the cargo ship crossing the Pacific, the sail continues to teach us a powerful lesson. True progress is not always about creating new power sources, but about learning to work in harmony with the immense renewable forces that have always surrounded us. This elegant dance with the wind, however, would be impossible without a tool that could withstand the immense forces it created, a tool that used tension to bind a ship together against the power of the sea. That triangular wooden framework supporting a Roman bridge is a masterclass in geometric strength. Long before engineers had equations for stress and strain, they understood that the triangle is the only rigid polygon, a shape that cannot be deformed without changing the length of its sides. By arranging beams into a series of interlocking triangles, Roman builders created the truss, a structure that could span impressive distances while supporting immense loads. This was not about using more wood, but about using it more intelligently. The weight of the bridge deck or the roof was no longer a burden borne by a single beam, but a force cleverly distributed. Each member of the truss was either in tension, being pulled apart, or in compression, being squeezed together, channeling the forces efficiently along the rigid triangular paths down to the sturdy supports at either end. This principle of load distribution is the very soul of modern civil engineering. You can see its evolution in the intricate stone vaults of medieval cathedrals, where the flying buttress acts as a kind of stone truss, countering the outward thrust of the massive roof. Centuries later, during the Industrial Revolution, engineers began to codify this ancient wisdom, giving us named configurations like the Warren Truss, with its repeating equilateral triangles ideal for railway bridges, and the Pratt Truss, which uses vertical beams in compression and diagonal beams in tension to create incredibly efficient frameworks for skyscrapers. The goal was always the same: to achieve the highest possible strength-to-weight ratio. This is why you find trusses in the skeletal wings of aircraft, where every ounce saved is critical, and in the modular frameworks of the International Space Station, which had to be launched piece by piece and assembled in orbit. Look at the exposed steelwork of a massive sports stadium, or even the wooden rafters in the attic of a modern home, and you are looking at the direct descendant of those Roman bridges. How is it that such a simple geometric shape can provide the backbone for our largest and most ambitious structures? It is a powerful reminder that elegance in engineering often lies not in complexity, but in finding the most fundamental, stable pattern to channel the forces of our world. This mastery of large-scale frameworks paved the way for a tool that brought perfection to the finest details, smoothing the rough edges of any creation. The rasping sound of steel on bronze was the sound of a rough edge being tamed. Long before the whir of electric sanders, ancient metalworkers relied on a simple handheld tool to refine their creations, the file. Since the Iron Age, these hardened steel bars covered in sharp, angled teeth have been the final word in precision, transforming jagged castings into perfectly fitted components and rough jewelry into smooth, wearable art. Blacksmiths through the ages developed an entire family of files for different tasks, from coarse rasps with individual teeth for quickly shaping wood, to delicate needle files whose fine cuts could trace intricate patterns on a lock mechanism. Each variety was a lesson in controlled abrasion, using the principle of friction to methodically scrape away minuscule slivers of material. This was not brute force, but a patient, skilled dialogue between the craftsperson and the metal, a process where the final fit and finish were literally carved by hand. The file's true genius lies in this gradual, controlled removal. In the forging of a sword, the rough blank from the smith's fire was just the beginning. It was the careful work with files that defined the blade's final edge, balanced its weight, and ensured the hilt fit the hand perfectly. This same meticulous process was used to create the complex internal tumblers of ancient locks, where a fraction of a millimeter too much or too little material would mean the difference between security and failure. This foundational action of scraping and smoothing has been automated and amplified in our modern world. The computer-controlled milling machine is essentially a robotic file, its spinning cutter head performing millions of precise, programmed cuts to shape metal blocks into engine parts. Even in the futuristic realm of 3D printing, the rough, layered surface of a freshly printed object often requires a session of manual filing and sanding, a post-processing step that proves some finishing touches are timeless. The tool itself has evolved with new materials, giving us diamond-coated files that can shape hardened glass and ceramics, and electronic file sets used by model builders to achieve a flawless finish on miniature parts. In an auto body shop, a technician might use a long, flexible file to check the contour of a repaired fender, ensuring every curve is perfect before paint. In a dentist's office, a set of microscopic files is used to adjust the fit of a crown or bridge, a modern application where the stakes for precision could not be higher. This ancient tool invites a powerful question for our own endeavors. How often does the success of a grand project hinge not on the bold initial strokes, but on the patient, meticulous refinement of the smallest details? The file teaches us that true craftsmanship is found in the final pass, the last adjustment that transforms something that merely functions into something that endures. And just as the file mastered the art of refining surfaces, another ancient tool would conquer the challenge of breaking through the earth itself, enabling us to reach the resources hidden deep below. The relentless rotation of a bow drill transformed friction into fire and solid stone into a hollow vessel. This simple tool, a precursor to every powered drill in your garage, harnessed two fundamental forces, rotation and downward pressure, to achieve what pounding or cutting alone could not. Its origins reach back to Neolithic times, when a sharp stone or shell tip was spun rapidly between the palms, or with a bowstring to bore holes in wood, bone, and soft stone. This was not merely about making holes, it was about unlocking new possibilities, from threading beads for adornment to assembling the first complex wooden structures. Roman engineers later perfected this with the auger, a tool featuring a helical fluke that pulled itself into the material, making it indispensable for shipbuilding, mining, and even early forms of dental work. Archaeologists point to drill cores found in ancient quarries and exquisitely drilled stone beads from Indus Valley cities as evidence of its widespread, sophisticated use across continents. The underlying physics is a masterclass in focused energy. The drill bit concentrates a tremendous amount of rotational force onto a tiny cutting edge, shearing away minute fragments of material with each turn. This principle of localized rotational cutting is the very same one that drives the massive rotary drill heads on modern oil rigs, chewing through miles of rock to reach fossil fuels, and the delicate surgical drills used in neurosurgery to carefully remove bone and access the brain. The evolution of this tool is a story of amplifying that rotational power. The hand-powered bow gave way to the crank and brace, which in turn was superseded by the electric motor, delivering consistent, high-torque rotation at the push of a button. Today, you can see this ancient lineage in a dentist's high-speed drill, which uses a precise, air-driven turbine to prepare a tooth for a filling, and in the laser drills that create microscopic holes in computer circuit boards, enabling the complex interconnections of modern electronics. From the ancient Egyptian craftsman patiently hollowing out a granite vase to the homeowner using a cordless drill to assemble a bookshelf, the fundamental action remains unchanged. We are still applying a spinning edge to penetrate and shape our world. This invites a powerful metaphorical reflection. How does the act of drilling, of penetrating a surface to see what lies beneath, mirror our own pursuit of knowledge and discovery? Whether we are exploring the layers of the past, the depths of a scientific problem, or the hidden potential within ourselves, the same principles often apply. Persistent, focused effort can reveal astonishing new layers. Having journeyed through these 23 revolutionary tools, a profound pattern emerges, connecting the workshop of an ancient artisan to the computer screen of a modern engineer. These 23 tools are not isolated relics, but a single, unbroken chain of ingenuity. From the Archimedes Screw lifting water with a simple twist to the Astrolabe mapping the heavens onto a brass plate, they share a common language of problem solving. Ancient engineers were not just builders, they were master innovators who looked at the natural world and asked how its forces could be harnessed, not conquered. They understood mechanical advantage, the elegant trade of distance for effort in the lever and pulley. They pioneered material science, mixing volcanic ash to create concrete that could harden underwater. They embraced principles of sustainability, capturing the endless energy of rivers and wind with water wheels and sails. Their greatest legacy is this foundational toolkit of principles, a set of ideas so powerful they have simply been refined, not replaced. We see this direct lineage everywhere we look. The fluid dynamics of the ancient screw now inform advanced hydropower turbines and gentle fish passage systems in modern dams. The complex gear trains of the Antiquity mechanism are the conceptual ancestors of the precision robotics assembling today's smartphones. The Astrolabe's method of projecting a sphere onto a flat plane is the very mathematical foundation for the GPS that guides your car, translating satellite positions into a street address. This synthesis reveals that our most forward-thinking fields, from renewable energy to space exploration, are built upon this ancient bedrock. Modern engineers tackling climate change are revisiting passive cooling designs from centuries-old architecture. Those designing life support for Mars habitats study Roman aqueducts and their efficient, gravity-fed systems. The drive for standardization that began with Roman nuts and bolts is now the global language of interchangeable parts, from USB connectors to spacecraft docking adapters. So what can we learn from this deep connection? Perhaps that the most sustainable solutions are often those that work in harmony with natural forces, not against them. As we face our own complex challenges, from urban water scarcity to the need for resilient infrastructure, the answers may already exist in the elegant efficiency of the past. This holistic view invites a final, powerful question. If ancient tools born from the needs of their time could echo for millennia and shape our world, what innovations are we creating today that will become the timeless foundations for civilizations yet to come? Our journey through 23 ancient tools reveals a profound truth, that human ingenuity is a continuous thread woven across millennia. From the simple twist of the Archimedes screw lifting water to the patient rotation of the bow drill piercing stone, these inventions were never just objects. They were crystallized ideas embodying timeless principles of leverage, flow, and geometric strength that modern engineers still rely upon every single day. These are not museum pieces gathering dust, but active, living influences. The same logic that guided a Roman aqueduct now manages the water flowing into your home, and the same understanding of tension that held a wooden truss together now stabilizes a suspension bridge against the wind. This heritage teaches us that the most powerful solutions are often deceptively simple, born from a deep observation of nature and a drive for practical elegance. Our smart cities and space-age materials are not a rejection of the past, but its ultimate refinement. Isaac Newton captured this perfectly when he wrote, "If I have seen further, it is by standing on the shoulders of giants." Every modern breakthrough is built upon a foundation laid by countless anonymous innovators, the original engineers who first turned a wedge into a chisel and a rope into a pulley. So the next time you turn a doorknob or charge your phone with renewable energy, take a moment to look for the echoes of antiquity hidden in plain sight. We would love to hear which of these ancient tools you find most fascinating. Was it the predictive power of the Antiquity mechanism or the sheer strength of the Roman truss? Share your thoughts in the comments below, and if you enjoyed this exploration into the foundations of our world, subscribe for more journeys into the mysteries of history. The giants of the past have given us a sturdy platform to stand on, and the view from here is truly extraordinary.